I'm going to talk to you about graphing and the fundamental principles that govern graphing, or the fundamental principle that tells you whether what you've done is correct or not. So this is the principle that must be adhered to by a correct graph. You'll always be able to check your work by making sure that this single principle is adhered to. So there's more than one way to understand graphs, to envision graphs, and there's all these different sort of aspects of what graphs are. So this is only really one way to understand what a graph represents, but this way is always adhered to when you've drawn the graph correctly. So that should allow you to determine whether what you've done is correct with confidence, because you understand the relationship between the equation and the graph itself. And it's really just one principle. There are several concepts involved, maybe, maybe not, but there's just one single principle. And the depth at which you understand that principle, or how well you have an understanding of that principle, will kind of set the road for you on how well positioned you are to understand the new information that's coming down the pipe. This description will be extremely detailed. So detailed that I risk it seeming either like cryptic or maybe even like esoteric, like incomprehensible, or only a certain type of person could understand it. But that's not the case at all. This stuff is completely accessible to you with a little bit of thought and work on your part. So there's no substitute for pondering ideas and concepts and thinking about how they work. So what I'm trying to do here is give you a framework with which to start from. This is by no means the only way to think about it, but it should give you a basis. And I'm also going to try to push the envelope of your understanding along the way in this presentation, so that you hopefully, the intention is so that you'll open your eyes up to that the implications of this stuff is really far-reaching. And just because you have a first cut understanding doesn't mean that you're going to be able to field a variety of questions for which these concepts are applicable to. The only way to gain that kind of understanding is through doing problems, thinking about it, applying the math, and asking questions that you can answer yourself by investigation, or asking your teacher questions, friends questions. It's by discussion. It's by being involved. The only way to do it is to be involved with the math itself. There's a difference between what I'm doing now and when I sit with a student. When I sit with a student, I can, or at least I try to, and I think I do a good job of it, I try to read them, and I can read that sort of deer in the headlights look, and that tells me, okay, I need to rephrase or restate or rephrase, or even maybe dial back the detail on occasion, only because the student isn't quite ready for it yet. But we're always working to get there. We're always working to deepen our understanding of the material. And nobody has an all-encompassing understanding of the material. I don't care who you are. You could be Einstein, and you're not going to know everything about graphs. That might seem like a reach, but I think you know what I'm trying to say, is that no matter in what area, there's always a problem that can stump anybody. So it's just the way it is. All we can do is the best we can, and that's all we should expect. That's all we should expect of ourselves. So let's get started. We need a framework for which to graph, and that framework is the rectangular coordinate axis system, also known as the Cartesian plane, which are just big words for something that's simple and you've probably already seen, but you need to know the mechanics of how this thing works. So I'm going to draw it real quick. And the rectangular coordinate axis system is two axes. We have an x-axis and a y-axis. We only put arrows in the positive direction, but you know, these are just mathematical conventions that most math people adhere to, so I try to adhere to them. But none of this is, you know, you don't have to put arrows in the positive direction. Later on, you might have a teacher that says, yes, you do have to, but right now I wouldn't worry about it too much. I just want to do it correct here, or what I believe is correct, or what I learned is correct by convention in mathematics. So this is the Cartesian plane, an x-axis and a y-axis, and every point on this plane has a unique address, and that unique address is its xy coordinate. So right here, that point is called the origin, and its xy coordinate is 0, 0. We're moving 0 in the x direction and 0 in the y direction, so we're just right there. But if I moved 1 in the x direction and 2 in the y direction and put a point right there, the coordinates of that point would be 1, 2. So this is the point whose unique address is 1, 2, 1 in the x direction, then 2 in the y direction. And the important thing here is to recognize that every point has a unique address. Every point is unique on this Cartesian plane. So, you know, pause and let that sink in, because that's significant to this presentation. So I really want you to, you know, understand that. And then, okay, now what is a line? Well, a line, I'll just draw a line here. We can think of a line as a collection of points. So how many points are on this line? And the arrows indicate that the line goes on forever in that direction and forever in that direction. So this line is of infinite length. And if I asked how many points are on this line, the correct answer, and I think it's easy to see, there's an infinite number of points on this line. So a line is a collection of points. How many points in a line? An infinite number of points. Let's see, what else did I want to say about line? Oh, 2 points define a line. So, I should say 2 unique points define a line. So it only takes 2 points to define a unique line. So, and what that means is that if you have 2 different points, doesn't matter where those points are, as long as they're not on top of each other. So they have to be unique points. If they were on top of each other, it just would be 1 point in space or on the plane. So they have to be unique points. Then notice that there's one line and one line only that goes through those 2 points. If I want to draw it, I would have to, you know, go through the, well, I missed the point. But you get the idea. 2 points define a line. So every line, you only need to find 2 points that are on a line to define that line. Okay? So that's what a line is. And this is the Cartesian plane. And I think I'm going to use this one for my example here. I guess I'm not. So I'm going to just erase this point, and then what I'm going to do is I'm going to draw the equation of the line 2x plus y equals 2. So we're going to do 2x plus y equals 2. And I'm going to use techniques that you may or may not know to draw this line, but I'm just going to go ahead and draw it because I'm really not concerned here with the mechanics of how we do it. I'm more concerned with the conceptual understanding of what's going on. You know, why is this the line that is that equation? How do you know that's the line that is that equation? So I'm just going to draw the line really fast. And I can see that, well, actually, there's a point on the line. And there's a point on the line. So as I said before, 2 points define a line. I found 2 points that are on the line, so I can draw the line connecting those 2 points. And this is the line. Sorry that it's not as straight as it could be, but I'm sure that's satisfactory. This is the line that represents an equation. So think about what I said before. This is a line. A line is a collection of points. This line satisfies that equation. What does that mean? That means you can choose any point on the line, figure out the x and y coordinate of that point. If you plug in the x coordinate for x and the y coordinate for y, this equation will be true. So let's find a point on here where that is true. So I'm going to say, let's see, that must be 2, -2. So I say that's a point on the line, and its coordinates are 2, -2. And let's check that in the equation. So if we plug in 2 for x, 2 times 2 is 4. And if we plug in -2 for y, we have 4 plus -2 is 2, and 2 equals 2. So that is indeed a point on the line. And that's going to be true for every point on this line. And there's an infinite number of points. So this graph is a pictorial representation of that equation. So it gives you a visual. This equation depicts a relationship between x and y. If you assign a value for x, you can find a value for y such that the equation is true. So this equation establishes a relationship between x and y. This graph is a pictorial representation of that relationship. So I really hope that makes sense. I mean, I think it's worth it to take. I mean, it's simple, right? It's a simple concept, but the implications of that concept aren't simple, and you can just fool yourself into thinking that you have a good enough understanding or a complete enough understanding, or you get it. That's it. You're done. You don't need any more. You don't need to think about it anymore. I assert that's never the case. It's never the case. It's never the case that you can say, I know everything I need to know about that mathematical concept or that mathematical construct or this, the implications of applying math this way or anything mathematically. It's just not the case that it's that simple. So, and I want to show you some of the implications of this. So I'm going to, push ahead, and if you get this, that's just fantastic that you get that. But let's go a little further and see if we can find some implications of this stuff. So I'm going to erase this. I'm going to change the label. I'm going to change the axes. And I'm not even going to have an equation. This isn't even going to be an equation. So I'm going to go to velocity and time. So we all, we've all experienced driving or riding a bicycle or whatever. You know what velocity is, or you know what speed is. You're going, in a certain direction at a certain rate of speed. So this is going to be the velocity, and this is going to be time. And let's say that we have 60 up here. You have a stopwatch. You click your stopwatch start. You're looking at your speedometer. You're a passenger in the car, and somebody else is driving. You guys are doing this experiment together. And right when you hit 60, you're going to keep it constant at 60 miles an hour. Right when you hit the stopwatch. Right when you hit 60. So we're going 60 miles an hour for an entire hour. So that's 1 hour right there. So how far have you gone? 60 miles an hour for an hour. That, it's so simple, you almost don't even want to think about this. Please think about this, because we want to see how this is descriptive of reality. And I know you already know reality. This is simple. So you already know the reality, but I still want to, look at this. So how would you figure out that you went 60 miles an hour? or I'm sorry, that you've gone 60 miles in 1 hour. Well, you would just do 60 miles per 1 hour times 1 hour. And you can see that, this also, reinforces your computational abilities by doing stuff like this, because units always have to work. So here we have 60 miles an hour times 1 hour, and the hours cancel. And we're just left with 60 miles. So that makes sense. We understand that. But what are the implications on the graph? What is the graph kind of telling us? I think that the graph is suggesting that we have 60 miles per hour and 1 hour, but we just multiplied them together here to get the distance. And our notions of what area is in just geometric figures, I'm just going to make a rectangle out of this. And we have 60 miles per hour. And we have 1 hour. I'm sorry, I drew that wrong. It's so easy to make careless errors. We have this length is 60 miles per hour. Whatever that means. It's kind of weird. That length is 60 miles per hour. But yes, that's what that represents. That's 60 miles per hour. This is 1 hour. And if you multiply those two together, which we just saw here, you get 60 miles. So that makes it appear that, or if you know from the computing areas of geometric figures, the area of this rectangle is 60 times 1. So, and that's 60. So it looks like, or this suggests that the area under the velocity versus time curve is the actual distance that you went. So I'm going to suggest that that's true. It certainly looks true here to me. But let's think about that. So what I want to do is, instead of going 60 miles an hour for the entire time, what if we started at 0 miles an hour and ended going 60 miles an hour? And we just did it at a constant rate of acceleration, constant rate of change of our speed. So we started at 0, and then, we're just going, 1 foot per hour is our speed, and then a mile per hour, and 2 miles per hour. And at the end of an hour, we're going 60 miles an hour. So by our discussion that we just had, I'm going to suggest or assert that the total distance that we went is the area under this triangle. I'm going to say, because of the discussion we just had, I think this makes sense. And I'm going to argue that it's true. So what I want to do here is I want to, I think same color. What I want to do is I want to break this up into intervals. So I'm going to go, the first half hour and the second half hour. And I'm going to estimate the distance that we've gone in the first half hour and the second half hour by drawing rectangles. So, and I think that's pretty easy to do because of the last example, we saw that the area of the rectangle is the distance. So I'm going to estimate it just by using the right-hand endpoints. So I'm going to estimate the area, or I'm going to estimate the distance that we went in the first half hour by this entire rectangle. And I'm going to estimate the distance that we went in the second half hour by this entire rectangle, by the area under this entire rectangle. So I think you can see that we're obviously, it should be obvious that we're overestimating the area of this triangle by taking the sum of the areas of these two rectangles. So what would happen if we decided to use more rectangles? To break it up, I broke it up into 2 intervals. Well, what if I want to break it up into 4 intervals? So I'm going to divide each of these 2 intervals in half. So I do that, and I get, by using the exact same method, right-hand endpoint. Now I'm estimating the area of the entire rectangle with 4 rectangles. And you can see it's a better estimate because I'm still overestimating, but I've left out now this whole block that we see. You can see visually that's an overestimate. That's part of overestimating this chunk and this whole block. They've been eliminated. So that's a better estimate than what I had before. I hope that's clear. It should be clear. So then, now we're going to do it again. So each of those intervals, I'm going to chop into 2 intervals. So, and that's going to look like this. And now you can see that we've actually eliminated even more of our overestimate. So we've eliminated this little chunk and this little chunk and this little chunk and this little chunk. We're still overestimating, but we've eliminated a portion of that overestimate. So we're like honing in on the actual area. So now we need to now use our imagination. And imagine you just continue doing that. You just do it again, and then you get these little, you'll actually eliminate this little chunk right here. And if you do this exercise, you'll see what I'm talking about, and I really hope you're following me right now. But imagine that you do that again and again and again and again, and you end up doing it you really have to use your imagination with this, but you end up doing it an infinite number of times, So you end up with an infinite number of super skinny rectangles, and each one of them is, let's see here, I wish I had another color. They're super tiny ones. The width of a line is way too thick to represent the width of these rectangles. So no matter how many you have, if you have a finite number of them, you're always going to overestimate. But if you let the number of them go to infinity, now your overestimation becomes 0, and your estimate becomes the area under the graph. And we can see that for each of those little rectangles, I'm just going to draw one of those little rectangles right here. If we take the height of that rectangle times the amount of time that went by, that would be the distance traveled for that one particular tiny rectangle, because that would be the area of that one particular tiny rectangle. So, if we did that and we kept on, making the width smaller, the error involved in that one rectangle goes down, and as the number of rectangles goes to infinity, we get the actual area under the graph. And we already know that the area of each one of those rectangles represents the actual distance traveled for that interval of time that that rectangle covers. So I think that this argument is pretty, relatively convincing that yes, if this line is indeed the actual velocity given time, then the area under the graph from 0 to 1 would be actually the distance traveled during that time. So I think that's a convincing argument. But by no means is that proof. I actually don't even know if I'm capable of proving such a thing. This is actually alluding to like Riemann sums, and we're actually knocking on the door of calculus right now. So this is a calculus concept that we're discussing right now, even though we started with just graphing. But I guess the point that I'm making is that these are the implications of what we're doing, and this is where it's going. So, or what you're learning, if you're just learning graphing, or wherever you are in your mathematical education, this is the kind of thought process that we're leaning towards. Excuse me. And with calculus, we actually can do an infinite number of tiny rectangles. We actually have computational methods for employing that and actually figuring out what happens if we actually did an infinite number of rectangles. There's ways to, I think it's somewhat easy to conceptualize that visually, but it's not so easy to see how you would write that down mathematically and actually represent it with symbols on paper. And calculus allows us to do that. So, but, there's a lot of understanding that goes into studying calculus. So what is the principle that I'm talking about that must be adhered to draw correct graphs? Well, that principle is that the graph is a collection of points. Every point has an x, y coordinate. If you plug in the x value for x of that point into the equation and the y value for y into the equation, you get a true statement, or the equation is true. You figure out what the left-hand side is, figure out what the right-hand side is, and you get agreement. That's what it means for the graph to accurately depict the equation. That's always true for every graph. So that can be used as sort of like a guiding principle. I mean, whenever you're confused, or if you ever get confused, you can always think about that principle. And that principle has the ability, in many instances, to guide your thought process back on track to what's really happening and what's not really happening, which we work hard to understand, reality, to understand what actually is happening. We're just kind of like trying to eliminate the noise and focus on what's true. And that's a really tough thing to do, especially getting started doing it is, I think, especially tough. So I hope that this presentation made sense. I hope you found it valuable. And I'm very much interested in any comments that you might have, positive or negative, agreement or disagreement. I've got plenty to learn. I don't think I made any gross errors in my presentation, but I certainly don't know everything. So I really would like to hear comments. And thanks for spending the time listening.